Hey guys, this is section 2.2, the limit of a function. Now let's just think about what a limit is in real life. Forget the mathematics of it. Imagine someone says to you, "Oh, I reached my limit." What it means is they've gone as like far as they can go, and they just can't go beyond that. Okay, so they've approached their limit, like they've slowly been approaching it, and now they're there, and that's it. They've had it. So that's in like real life the way we use it. In mathematics and calculus, when we think about a limit, it's a value that a function approaches. Now, notice I said the word approaches, and that's going to be a key when we like go further into into a limit. But let me kind of explain what that means. Let's say we have a curve like this. Say this is our curve. This is like x equals 0. This is x equals 1. And we want to find out what is the limit as the graph approaches the x value of 1. So what we can think about is we can look at the graph and we can say, all right, so from this side, the graph is approaching this value. From the left side, the graph is approaching also this value, so that must be our limit. So a limit is going to be a value that the graph approaches. Now in this case, the graph contains that value, so that's one of our scenarios. Let me give you another scenario. Let's take a look at this scenario here on this graph. So we have this line, but the line is undefined at the point 1, -1. The little open circle means that the line is, this function is undefined. The value of this function doesn't exist. So if I say, what's x equals 2, you would say, if x equals 2, the y value is 0. I can ask you, well, if x equals to 0, what is the y value? Then we can say the y value is -2. But if I ask you, what is the value of this function when x equals to 1, then we would say it's undefined. The function has no value at x equals 1. So in this case, we can still have a limit because whatever point this graph is approaching, so as the graph approaches the x value of 1, we can see that the y values are going to be approaching -1. Okay, they're going to be approaching this y value, which is -1. So the limit does exist. The limit is -1. The graph doesn't contain that value, but because the graph approaches -1, that's the limit. So when we think about limit, we're just thinking about what is the graph approaching. It doesn't actually have to contain that point. So an informal definition is as x approaches a value of c, so in this case, like the c value is 1. The limit of f of x is L, written as the limit as x approaches c of f of x equals to L. So what it means is if all the values of f of x are close to a y value of L, so this is the y value here. So as the graph approaches an x value of c, if the y values approach a y value of, in this case, L, then that is the limit. So sufficiently close would consist of values that are less than or greater than c. So if x is c, we're going to be looking at values to the right of c and to the left of c. And so for a limit to exist from both sides, from both the right and the left, the graph has to approach a certain value. And that determines the limit. Okay, so that's kind of the informal definition. Let's talk about one-sided limits. So one-sided limits, this terminology, we have limit of f of x as x approaches c with the little minus sign. This means that we're going to be looking at the graph as x approaches c from the left or from -infinity. So we're going to look at the values coming from -infinity. When we have the limit as x approaches c from the positive side, we're going to be looking at the limit from the right or as we approach c from +infinity. So this is +infinity. So when you have c with a little plus sign, we're looking at the graph coming from +infinity towards c. So that's an idea of one-sided limits. Okay, here's a theorem, and then we're going to get into some examples. So this theorem states that as x approaches c, The limit of f of x is L if the limit from the left side exists and the limit from the right side exists, and both limits are L. So let me give you an example of this. So here's an example. So I'm going to show you a case where the limit does exist and a case where the limit does not exist. I'm going to give you both cases. So here's a case where the limit does exist. So we have this graph, and we have 1, 2, 3, 4, 1, 2, 3, 4. And what I'm going to do is I'm going to sketch a curve. So my curve is going to look like this. I'm just kind of making something up here. Now, I'm going to say what is the limit of f of x as x approaches 2. Actually, let's go with 2. So by definition, we're going to look at the graph of f of x as x approaches c, in this case 2, from the negative side. Okay, so now I'm going to approach the graph from the negative side, from this side. So if I follow the graph from the negative side, as we approach 2, the graph is approaching this value right there, which is approximately, I'm just going to say this is like 1.9. I'm going to approximate. So from the left, so as x approaches from negative infinity, the graph approaches a value of 1.9. Now, the other side also has to be true. So as limit of f of x approaches c from the positive side, so from this side, from positive infinity, as the graph approaches x value of 2, we approach the same exact y value, which is 1.9. So the limit of f of x as x approaches 2 is going to equal to 1.9. Okay, so this is, in this case, the limit does exist. Let me give you a scenario in which the limit does not exist. So here's another example. So we have our graph once again. Now this graph is going to be a piecewise function, which means it's going to be split up into different parts. So from the left, the graph looks like this, and then from the right, the graph looks like this. Okay, so now let's think about this. We want to find the limit of f of x as x approaches -1. We want to know what is that equal to. So let's take a look at the x value of -1. Which is here. Okay, so what happens to this graph as x approaches -1 from the left? So we're going to look at the first case from negative infinity. The y values approach this point, which is 0. As x approaches -1 from the right, from positive infinity, the graph has a y value of like 3.8 or whatever that is. So because from the left and right, the graph is approaching 2 different values, the limit does not exist. So in this case, we would say DNE, which means that the limit does not exist. So that's what this theorem says, that for a limit to exist from both sides, the limit has to approach the same y value. So now let's get into some details, limits of polynomial functions. If p of x is a polynomial function, then you can just use direct substitution to find the limit. A polynomial function is something like x squared minus 3x plus 4, where all the exponents are integers, and like we have no negatives, we have no fractions for exponents. That's a polynomial function. So for example, if I want to find the limit as x approaches 2 of x squared minus 3x plus 4, I simply do direct substitution, plug in 2, and I get a limit of 2. Because polynomial functions are continuous, kind of like this, so from both sides, they're going to approach the same value, and that value is what happens when you just plug in the x value into your function. Okay, now we're going to determine a limit using a couple of different ways, one numerically, and the other one is graphically. So to determine c numerically, we're going to make a table of values with inputs both to the left and right of x equals a. X equals a, this is what we're approaching. That's the x value we're approaching. And then we're going to evaluate the outputs. Based on that, we're going to determine does a limit exist. So here's an example. We want to find the limit, if it exists, by calculating the function at the given numbers. So our function is f of x equals to cosine of 3x minus cosine of x over x squared. And we want to find the limit as x approaches 0. So notice that we're going to have x approaching 0. So 0 is going to be like kind of in the middle here. So I'm going to say this is going to be my 0. So what we're going to do is we're going to be, I'm going to have 0 like down here. So we're going to be approaching 0, starting from a number like that's far away from 0, and we're going to get closer and closer and closer. Now, please do not do this by hand. Do not do it by hand. Use technology. So you can use Desmos.com, which is what I recommend. If you don't want to use Desmos, you can use a scientific or graphing calculator, but do not do it by hand. It takes too long. So I recommend using Desmos.com. So in Desmos, you would put in this function cosine of 3x minus cosine of x over x squared, and then you would simply plug in these values. So if I plug those in, so I have my I have a screenshot of Desmos here, and we can see that so first, put in the function and then just put in your values. Make sure that you're in radian form in Desmos, not in degree form. So go to the settings and make sure you change the settings to radians. And if you plug it in, we can see that the y values are going to get closer and closer and closer to -4. So what we can say is that the limit of this is going to be -4. So think about limit as which value is the graph approaching, not necessarily hitting. Okay, now let's do it graphically. So to determine the limit graphically, you would graph f of x, which is done for you, and you would determine the behavior to the left of x equals a and to the right of x equals 8, and then determine whether the limit exists. So let's take a look at f of 8. So let's focus on this value of x, which is x equals to 8. And I'm going to use a different color. So we're only going to focus on this point, okay? We're going to focus on this value of x. And we're going to look at, for the first example, we're going to look at what happens to the graph as x approaches 8. If a limit exists, it's going to approach the same value from both sides. So at 8, if I look from the left side and the right side, it's approaching 5. But the first question doesn't actually ask us for the limit. It just says what is f of 8. F of 8 means the value of the graph when x equals 8. Notice it's not even asking us for the limit. So the value of the graph when x equals 8 is going to be this value, which is 5. So f of 8 is equal to 5. Now the next one asks you for a one-sided limit. So it says, what is the limit of this graph as x approaches 6 from the left side? So now let's take a look at x equals to 6, which is here. Okay, this is the x value of 6. And we want to approach this value from the left. Okay, so I'm going to look at this value. So this is x equals 6 right here, this x value. And I'm going to approach it from the left. So coming from the left, it's going to approach this y value, which is 4. Okay, the next one, we have x equals 2 approaching from the right. So take a look at x equals 2, which is going to be this point. I have the little yellow line there, and it's approaching from the positive side. So I'm only going to focus on this graph close to, I don't care about the right side. I only care about the graph close to 2. So close to 2, x is approaching, y is approaching 2. So the limit is going to be, from the right side, is going to be 2. And the plus means I'm only looking at it from the right side. And then finally, the question is, what is the limit as x approaches 1? As x approaches 1, notice it doesn't give you a direction. It doesn't say from the positive or from the negative. So in that case, we have to look at it from both directions. Okay, so here's x equals 1 right there. So we have to look at the graph coming from the left and coming from the right. So let's first take a look at the graph of f of x as x approaches 1 from the left side. So coming from the left side, this is x equals 1. From the left side, this is where the graph exists. So from the left side, we have a limit of 4. Now let's take a look at the limit as x approaches 1 from the right side. So from the right side, the graph is here. From the right side, the limit is 1. So the limit as x approaches